This is Lab 1, Charged Tapes. Okay, to start off, the purpose of this experiment was to determine the amount of excess charge on one piece of charged tape. We found that the tape had a charge of approximately 8.18 times 10 to the negative 9th coulombs and a deficiency of about negative 5.11 times 10 to the 10 electrons. So the main physics ideas that we cover in this lab is Newton's second law, which is F equals ma, where gravitational acceleration, g, is 9.81 meters per second squared, and electric force is Q times Q1 Q2 divided by R squared, where K equals 9 times 10 to the 9th, which is the same thing as 1 over 4 pi epsilon naught. So we know that like charges repel, but opposite charges attract, and the charge of an electron is negative 1.6 times 10 to the negative 9th coulombs. We know that the mass of the clear tape is approximately 1 gram per meter, or 0.001 kilograms per meter. So we assume that the charge is equally distributed throughout both tape pieces, which allows us to draw a simple free body diagram to model the forces on the upper tape. We also assume that the two pieces of tape will have the same charge, which makes our calculations a little bit simpler and possible. And we assume that air resistance and other outside forces are negligible for this experiment. So our system consists of tapes A and B, and the meter sticks, and the surroundings is everything else. So our initial conditions is that two pieces of tape are stuck on top of a lab desktop, and a second piece of tape is placed on each. This top piece is called the U tape. Tapes A and B are measured to be 0.17 meters long. We see in this free body diagram that the only forces acting on the tape is the electric force and the gravitational force. So part 1 of our experiment, the top tapes are quickly removed from the bottom tapes, and we test them for charge by bringing a hand near the tapes. We found that an interaction indicates that they are charged. When two U tapes are placed near each other, they repelled each other because they were created by the same process, and therefore they have the same charge, and we know that like charges repel. The charged U tape was attracted to a neutral object because of electrostatic induction, and it was attracted to the negatively charged plastic pin, which means that our U tape must have a positive charge. Okay, so part 2 of our experiment, we have the same conditions from part 1, and after we separate the U tapes from their bottom pieces, we place one in between two meter sticks, and the second is held underneath. We then bring the bottom tape up, and we measure the displacement of the top piece. We know our F net in the y direction is 0 because the acceleration in the y direction is 0, which means that the forces must be equal. The forces of gravity and the electric force must be equal. We know the mass of the tape because of the things showed earlier, so we can find our mass to be 0.00017 kilograms and the gravitational force to be negative 1.668 times 10 to the negative 3 newtons. We're given the force for an electric force, which is K times Q1 Q2 divided by R squared, and we know K. But because we are assuming that the charges on the tapes are equal, we can simplify it to K times Q squared over R squared. Then we solve for Q, and we get square root FR squared divided by K. And we substitute on our known variables, and we get the charge of our tape is 8.818 times 10 to the negative 9th coulombs. We can solve for the electron gain by dividing the experimental charge by the charge of an electron. So we get negative 5.11 times 10 to the 10. And since our result is negative, we know that electrons must have been lost. So part 3 of the experiment, we can find the number of atoms on the tape by dividing the area of the tape by the diameter of the atom squared. You can see the calculation here, and we end up getting 6.32 times 10 to the 5th as our ratio, and 3.23 times 10 to the 16th atoms. Okay, so here we see the code for the experiment. I just coded what I described earlier as our calculation, so g-force, electric force, yada yada, and we end up getting this result, which supports what we have analytically found, and we see that the forces on the upper piece are gravitational force and the electric force, which matches our free body diagram. Okay, so some possible sources of error. The assumption that the tapes had equal charge could be incorrect. We don't know for certain. And the charges of the tapes could have been impacted by our handling of the tapes. So what if the electrons had positive charge and protons had negative charge? What would change about the observations I made with the tape and the other charged objects? So if the electrons had a positive charge, the tape would likely gain electrons instead of lose them because of its tendency to be more positive. The physical aspects don't actually change because we're not changing the material, we're only changing whether electrons are positive or negative. So why is it important to handle the charged tapes as little as possible? And what happens when the charged tapes come in contact with our hands or other objects? Well, it's important to handle the charged tapes as little as possible because they tend to be negative, so interacting with other objects will cause the tapes to pick up more electrons from interacting with these other objects, which will change the results we get.